Now at this stage, I'm not going to go integrating log functions. So at this stage, all we want to look at is going back. So we ended up with derivative on function. So let's look at, okay, now let's integrate derivative on function. Logically, we'll go back to where we started from. So if I have it in that form, I see the fraction, it's a fraction, and I notice, oh, derivative on function, then I know it's going to be a log. But notice, it's technically the log of the absolute value of function x, and I'll explain why in a little bit. So I see this. I go, all right. Maybe the first temptation is to go, oh, let's put this in index form. When we put this in index form, we get 7 minus 3x to the power of negative 1. And when we integrate, we add 1 to the power over the power. That's just created a problem because that new power is the power of 0. And you can't put that 0 on the bottom of the fraction. So if you see that, and you, for some reason, I don't know, one of those quick mistakes you make when you're working too quickly, and you go, oh, hang on, that's when a little triggers, you go, oh, hang on, must be a log situation, that's what's happened here. Let's create the derivative on top. I want negative 3 on top. Balance it out, negative 1/3 out the front. I now have derivative on function, so I know it goes back to the log of that function, so the log of the absolute value of 7 minus 3x. Okay, let's just do another one. So same idea, we want to create the derivative on the top. So 8 would be on top, put an 1/8 out the front. I know it goes back to the log of that function. But that's all right. Notice, if the power on the top is 1 less than the power on the bottom, again, good chance you're talking derivative on function, because when we differentiate the polynomial, the power will come down by 1. It should be 6x to the power of 5 for us. Now balance it out. Now you'll notice I didn't put the absolute value symbol in. Why? Sorry, say that again?
X to the power of 6 plus 2 is always positive.
That's right. I don't need the absolute value symbol because it doesn't matter what number I substitute in for x, I will get a positive number there. And that is why technically it's the log of the absolute value. You see, if you look at your, there it is, hyperbola, integrate that and people go, oh, it's log x. Well, that's got a little problem, hasn't it? Because if I want to integrate from, say, negative 2 to negative 1, log of negative 2, well, hang on. You can't do it, but clearly it has a value, because look, there's the area, it has an area, it must exist. That's why it needs to be absolute value. Reality, though, is that you don't when you're actually doing your calculation, because think about it, sure, you can't find the log of negative 2, so I was going from negative 2 to negative 1, and you can't find the log of negative 1, but what would you be doing in your calculation? You'd be going the log of negative 2 minus the log of negative 1, you'd use your log laws and say, oh, that's the same as the log of negative 2 over negative 1, becomes a positive number, you get an answer. So with definite integrals you can tend to get away with it. It's safer, if you're just unsure, just put the absolute value signs in, what's it matter? You know, it's not going to change the answer. 1 on 5x then. I would like to create the derivative on top, which is of course 5, put a 5th out the front. It becomes 1/5 the log of 5x. Of course I could have done it another way. I could have factorised that 1/5 out the front of the integral symbol, and then I'll integrate 1 on x. Hang on. I got a different answer. Or do I? They are in fact the same answer. They just look different. Again, why?
The value of c is different because you can just extract.
Right. This c is not the same as this c. Again, if you used your log laws, you could rewrite this as a 5th log 5 plus a 5th log x, and the 5th log 5 is just a constant value. So if you like, the second c over there on the right would actually be equal to 1/5 log 5 plus the c of this first example here. So they are indeed the same thing. It does make life interesting when I'm marking, say, your work, or indeed when you're checking your answers. You might look at the answer and it's not what you got, but does that mean you actually got it wrong? Maybe they've just written it in a different form and they are actually equivalent answers. 4x plus 1 on 2x plus 1. So I'd say, well, okay, look, it's got to be a log situation because there's 2x plus 1 on the bottom. And again, you go to the power of negative 1, I've got an issue. But I can't create the derivative on the top because I've got this x on the top. So if you ever see something where the order of the numerator is the same or bigger then the order of the denominator, do a polynomial division and break it up into two things, or three things depending on how many terms you've got. I don't know if we really need to do a polynomial division, but if we did, here's our polynomial division, we can work it out. But yeah, I could rewrite that fraction as 2 minus 1 over 2x plus 1, and now each of those things I can handle. Now the first one, well, 2 just goes to 2x. The second one would be minus a half log of the absolute value of 2x plus 1. Let's do a definite one. Nicely, the numerator is already the derivative, so I don't have to do anything here. It goes to the log of x squared plus 1, and substitute in the 2, substitute in the 1, use my log laws, I get the log of 5 on 2. Just got to be careful with definite integrals, right? You cannot integrate across an asymptote. So for example, again with our hyperbola over there, if I had said, well, what's the integral from minus 1 to positive 1? That's going across the asymptote. Can I get a value for that? Well, think about what integration's measuring visually. Measure ring area. What's the area of that going to be when that's going off to infinity up there, that's going off to infinity up there? So this is where we get problems. Right? Just need to take care with that. Sometimes you'll see questions like this, and it's sort of giving you a big hint on how to do the integration. They'll ask you to differentiate something first, and it gives you a clue, because to integrate you can usually go backwards. So differentiating x cubed log x. Okay, write down the first, diff the second, plus write down the second, diff the first. We end up with that. Now it's saying integrate x squared log x. Well, I don't know how to do that, but I do know how to integrate x squared plus 3x squared log x, because we just differentiated something and got that. So logically, if I integrate, I'll go back to what I started with. The only difference being I'll make it the log of the absolute value of x rather than the log of x. Now, instead of just a line where I'm saying here's the question, here's the answer, I'm now looking at it and thinking this is an equation. I want to make the integral of x squared log x the subject of this equation. Now I'll move the integral of x squared dx to the right hand side. Well, I now can work out 3 times the integral. Therefore, my actual integral will be 1/3 of that right hand side. So I'll end up with 1/3 of x cubed log x. And when I integrate x squared, I get 1/3 x cubed. Divide that by the 3, I now have 1/9 x cubed. So why? Why is it the log of absolute function x? I mean, I showed you visually over there with the hyperbola y, but mathematically, why? We know the domain of our log function is greater than 0. We know that. So, alright, if I'm dealing with positive numbers, I don't have an issue. If I know whatever I substitute in, I'm going to get a positive, fine, that's log of function x, not a problem. No problems with the domain. But hang on, if I've got a negative number, then when I get at my answer of log of function x, I have an issue, because the log function is now undefined. Can't find the log of a negative number. It's alright, I can fix that problem via substitution. How about I let u equal negative function x? Now if that's the case, then du would be minus the derivative of function x dx. In other words, I could now rewrite this integral as minus du over minus u. The negatives will cancel, and I now have the integral of du on u, which I know is log u, but now I don't have an issue, because u will always be positive. Remember, u is the negative of function x. If function x is always negative, then u has to be positive, so I don't have an issue. Substitute back in, then it's the log of negative function x. Okay, so what we basically said is that's our definition for the integral, writing it as one of those split functions, which actually is very similar to something else. Remember the definition for absolute value? That was actually our definition for absolute value. Essentially the same thing, which means it's the log of the absolute value of function x. There we go. Okay, that shall do us for theory today.